This is a presentation on the book Advances in Financial Machine Learning by Lopez Prado. This was done in the context of the course of Financial Data Science taught by Professor Afshin Ashofte. The work was performed by Rodrigo Monteiro. The behavior of prices observed in financial markets is such that financial series exhibit low signal-to-noise ratio. Additionally, to achieve stationarity, returns have to be calculated on a time series by differentiating, at the cost of erasing all of its memory. While stationary, these returns data series are of poor usage for prediction purposes, since integer differentiation leads to memory erased series that will likely lead to false discoveries. In this chapter, the author argues that, alternatively, researchers could fractionally differentiate a time series. This technique would lead a time series to be stationary while keeping some of its memory. A stationary time series is defined as a stochastic process whose unconditional joint probability distribution does not change when shifted in time. Consequently, parameters such as mean and variance also do not change over time. Due to different characteristics of financial markets, prices tend to vary in unpredictable ways. This makes most financial time series non-stationary and unfit to use for future estimation without some sort of transformation. To this effect, if someone wants to precisely forecast the future path of some financial time series, the noise has to be removed, and integer differentiation is the usual way of achieving this goal. This, however, leads to memory-less datasets that, while stationary, are missing important information, useful for a model's predictive power. In this way, the solution is finding the ideal differentiating step between 0 and 1. That guarantees stationarity and increases the model predicting power. However, there is a trade-off between stationarity and memory. That is, an increase in the level of differentiation will lead to an increase in stationarity. Consequently, it will also erase some of the series memory, which makes the task of finding the ideal value of differentiation that guarantees the best balance between the two variables. Two topics are discussed: the premise of making non-stationary series stationary through integer transformation, the notion of fractional differentiation applied to the predictive time series analysis. Besides that, the literature on this subject has been surprisingly scarce, adding up to 8 journal articles, written by only 9 authors. Considering the backshift operator applied to a matrix such that the result is a lagged series, it is verified that for the particular case of k equals 2 is seen that for the general case of x plus y to the power of n, it is true that and for a real number d, the binomial series is derived. As such, in a fractional model, the exponential d is allowed to be a real number, and the following formal binomial series expansion is derived. For the series to keep its memory with a real non-integer positive d, we have that xt is the cumulative sum with weights w and values x. For positive k and w0 equals 1, the weights can be generated iteratively as the figure plots the sequence of weights used to fractionally differentiate the series. For d equals 0, all weights are 0 except for w0, which is 1. This is the case when the series remains the same. When d equals to 1, It is the case of a regular first-order integer differentiation. Between these two cases, weights are negative and greater than -1. The right picture shows how the weight sign vary for D between 1 and 2. This alternation of the sign of the weights for even and odd values of k will be discussed in the next topic. From the above result, it is concluded that k is greater than D. As such, the weights converge asymptotically to 0 from the left when integer D is even, and from the right when integer D is odd. When D is a fractional value, the weights are between -1 and 0 for all k greater than 0. This alternation of weight signs is necessary to make the time series stationary, as memory wanes or is offset over the long run. Two alternative implementations of fractional differentiations will be applied: the standard expanding window method and a fixed width window frac-diff method. To fractionally differentiate the finite time series in practice, because of data limitations, the fractionally differentiated value cannot be computed on an infinite series of weights. This means that the initial points will have a different amount of memory compared to the final point. For each I, we can determine the relative weight loss. Given a tolerance level between 0 and 1, we can determine the value I star such that lambda I is smaller or equal than that level, and lambda I plus 1 is greater than that level. This value corresponds to the first results where the weight loss is beyond the acceptable threshold, for example, a level of 0.01. Lambda I star depends on the convergence speeds of Wk, which in turn depends on D. Hence, it is suffice to drop x1. As D tends to 0 plus, I star increases, and a larger portion of the initial xt needs to be dropped in order to keep the weight loss smaller than the acceptable threshold. This figure shows the E-mini S&P 500 future trade bars of size 1E4 rolled forward, fractionally differentiated with parameters D equals 0.4 and tau equal to 1 on the top, and parameters D equals 0.4 and tau equals 1E minus 2 on the bottom. The negative drift in both plots is caused by the negative weights that are added to the initial observation as the window is expanded. When there is no control for weight loss, the negative drift is extreme, to the point that only that trend is visible. The negative drift is somewhat more moderate in the bottom plot, after controlling for the weight loss. However, it is still substantial, because values are computed on an expanding window. This problem can be corrected by a fixed width window, as shown in the next topic. Alternatively, fractional differentiation can be computed using the fixed window. That is, dropping the weight after the modulus of Wk falls below a given threshold value, tau. This is equivalent to finding the first I star such that modulus of W star greater or equal than tau and modulus of t plus 1 smaller or equal than tau, setting a new variable, Wk. This procedure has the advantage that the same vector of weights is used across all estimates, hence avoiding the negative drift caused by an expanding window's added weights. The result is a driftless blend of level plus noise, as expected. The distribution is no longer Gaussian as a result of the skewness and excess kurtosis that comes with memory. However, it is stationary. The next figure presents an implementation of this idea. Consider a series. Applying the fixed width window frac-diff method on this series, it is possible to compute the minimum coefficient D star such that resulting fractionally differentiated series is stationary. This coefficient quantifies the amount of memory that needs to be moved to achieve stationarity. The next figure illustrates this concept. On the right y-axis, it plots the ADF statistic computed on the E-mini S&P 500 future log prices, rolled forward using the ETF trick, downsampled to daily frequency. On the x-axis, it displayed the d-value used to generate the series, on which the ADF statistic was computed. The original series has an ADF statistic of minus 0.3387, while the return series has an ADF statistic of minus 46.9114. At the 5% confidence level, the test's critical value is minus 2.8623. The ADF statistic crosses that threshold in the vicinity of d equals 0.35. The left y-axis plots the correlation between the original series and the differentiated series at various d values. At d equals 0.35, the correlation is still very high, at 0.99995. This confirms that the procedure introduced in this chapter has been successful in achieving stationarity without giving up too much memory. In contrast, the correlation between the original series and the return series is only 0.03, hence showing that the standard integer differentiation wipes out the series memory almost entirely. The example of E-mini futures is by no means an exception. The next table shows the ADF statistics after applying FFD on various values of D for 87 of the most liquid futures worldwide. In all cases, the standard D equals 1 used for compounding returns implies over-differentiation. In fact, in all cases, stationarity is achieved with D smaller than 0.6. In some cases, no differentiation at all was needed. This chapter showed the technique used to ensure that a time series can be stationary and preserve the memory essential for machine learning prediction algorithms. By fractionally differentiating, a set of weight is given to past observations, with the values tending to zero, while using an expanding window leads to a negative trend in the presented example. Setting a limit level for the modulus of the weights solves this issue and delivers a driftless blend of level plus noise. To conclude, the author suggests following these steps. First, compute a cumulative sum of the time series. This guarantees that some order of differentiation is needed. Second, compute the FFD series for various d between 0 and 1. Third, determine the minimum d such that the p-value of the ADF statistic on FFD falls below 5%. Fourth, use the FFD series as your predictive feature. Thank you.